So welcome to this lecture on statics ME106, and this probably is the last lecture related to chapter number 10. And here we are solving a problem 10-120 of your textbook RC Hibbeler 12th edition. And so it says that the pendulum consists of the cylinder rod OA. Okay, we have a cylinder rod OA which has a mass per unit length of 3 kilogram per meter. The thin disc has a mass per unit area of 12 kilogram per meter square. So it's basically kilogram per meter square. And we first have to find the center of mass y bar. Okay, so this y bar measured from this point O. So this point O is the reference point or the supporting point of this structure. And then we have to calculate the moment of inertia of the pendulum of this compound pendulum about an axis perpendicular to the page and passing through G. So we have to calculate the moment of inertia about an axis that is passing from the center of mass of this body. Okay, about this axis, which is perpendicular to the page and passing from point G. So you have to note that the moment of inertia MOI is always calculated for a volume. So this given figure here represents a volume. We have a rod that has a volume, and we have a disc, a thin disc that has some kind of a volume. So it is a composite volume actually. It's not composite area. The last problem that we did from chapter number 10 was related to the second moment of area, and second moment of area is always calculated for the cross section. But moment of inertia is not related in any way with the cross section area. It is related with the volume. Right. So let us name the segments that are given to us in this figure. So we say that this rod OA is actually volume number 1. Okay, sub volume or constituent number 1. Then this larger disk is volume number 2, and this smaller disk, which is actually being extracted from the figure or subtracted from the figure, is volume number 3. So we are considering this point O as our reference. So everything will be measured from this point O, which is also the supporting point for this pendulum. And from this point O, we will going to first calculate the the center of mass for this entire volume, which is composed of these 3 sub volumes 1, 2 and 3. So we have calculated center of mass, centroid and center of gravity in chapter number 9, and we did one problem, I remember, using volumes. So in this problem we're going to use the same concept. So before we begin calculating y bar m, we will going to note that the center of mass of the individual volumes is offset from the axis that is passing from point G. So this red axis that is passing from point G, about this red axis we have to calculate the moment of inertia of this entire volume. And we see that this entire volume consists of volume 1, which is of rod, volume 2, which is of disc, and volume 3, which is of disc that has been subtracted. And the center of mass of these individual volumes, these constituent volumes, they have their own center of mass. Okay, so they have different center of mass compared to this G. So this G is the center of mass of this entire volume. Okay, but of course we know that the center of mass of this rod maybe lies here, and the center of mass of these disks will lie at their centers. So we note that these centroids, these centroids or center of masses, are basically at a distance from this axis about which we want to calculate the moment of inertia. Okay. So this means that we will be using parallel axis theorem. Without the knowledge of parallel axis theorem, we cannot calculate the moment of inertia of this entire volume, because you see, right, even though this figure seems to be symmetric about the vertical axis, okay, but we are not actually concerned with the vertical axis. We are actually concerned with this red axis, which is perpendicular to the page and passing from point G. So about this axis we want to find the moment of uh, inertia. And as soon as we look at this axis, this red axis, we realize that the centroid of the rod is not located on this red line, but it is located somewhere here. And similarly, the centroid of this disc is not located at the line that is passing from point G, but it is located somewhere here at its center. And so we see that clearly there exists some sort of a distance between these axes. So they are moment arms, and therefore we have to use the parallel axis theorem, right? So the concept of Boolean algebra in case of moment of inertia can only be used if the center of mass of individual volumes coincide with the center of mass of the composite volume. So this means in this problem, this second point is not fulfilling. Okay, therefore we cannot use Boolean algebra in this problem, since the centroids of individual volumes are separated. They are acting away from this axis that is passing from G, about which we have to calculate the moment of inertia. So we cannot use Boolean algebra, we have to use parallel axis theorem. But suppose that you have this kind of a body, okay, given to you, right? And you see that uh, if I ask you to calculate the moment of inertia about this axis, sorry, the perpendicular axis, the z axis, so you will notice that the centroid, or the center of mass, right, the center of mass of the outer disk lies at z dash axis, and the centroid of the inner disk also lies on the same axis. So in this case, since the centroid of, you know, the composite volume and its constituent volumes all lies on the same axis z dash, about which I am calculating the center of the moment of inertia, I can use Boolean algebra. So I will going to calculate the moment of inertia of the outer disk, and then I will going to subtract moment of inertia of the inner disk from the outer disk to get the moment of inertia of this composite shape. Right. Similarly, if you are given this kind of a object, okay, and I ask you to calculate the moment of inertia about this axis, so you can exactly repeat the same thing. You can calculate the moment of inertia of this outer square, okay, about this axis, because it has a centroid lying on this axis only, and you can then calculate the moment of inertia of this inner square. The centroid lies on the same axis here, and the centroid of the composite shape also lies on this axis. So there are no moment arms like these. Therefore, I can use Boolean algebra for this case. But as soon as the centroids will going to be offsetted from the axis about which you are calculating the moment of inertia, okay, you cannot actually use Boolean algebra. You have to rely on parallel access theorem. Also, you see, if I ask you to calculate the moment of inertia about this point, or about an axis that is passing from this point, okay, then you can realize that the centroid of all these sub volumes are being offsetted from this axis that is passing from point O. So again, you will be using parallel axis theorem to calculate the moment of inertia of this composite volume about point O. Similarly, if I ask you to find the moment of inertia of this composite shape about an axis that is passing from this, that is passing from this point O, then you can realize that the centroid of all these constituent volumes are being offsetted from this axis. Okay, so there exists a perpendicular distance between the two axes, and therefore again you have to use the parallel axis theorem to calculate the moment of inertia of this composite shape about this axis that is passing from point O. So these 2 points you have to remember, they are very same as we noticed them in the previous problem as well. So first of all, we have to calculate the center of mass of this given body, because without calculating the center of mass, we cannot calculate the moment of inertia. We require this value y dash. So as chapter 9 suggests us that we have to basically make a table now in order to calculate the moment of, the center of mass. Okay, so the center of mass measured from O, this y dash, okay, will be divided between these three sub volumes, that is the rod, the outer disk, and the inner disk. So I'm taking one as the rod, and I have to find out its mass. So its mass will be, okay, the rod has a, it is given that the rod has a mass per unit length of 3 kilogram per meter. So you multiply 3 kilogram with the length of the rod, that is 1.5, and you will get 4.5. So the mass of the rod is 4.5 kilogram. Similarly, the mass of the outer disc that has a radius of 0.3 meter will be 12 kilogram per meter square. This is kilogram. So 12 kilogram per meter square multiplied by the area of the cross section area of the outer disc, which is pi r square. So pi times 0.3 square and multiplied by 12. So this gives you 3.392 kilograms. Okay, and similarly the this disc that is being subtracted, because it does not actually exist in the actual body given to us. So we calculate its area. The radius is 0.1. So again, pi times square of 0.1. Pi r square is the area of the cross section area of the circle, and circular cross section area. So pi times 0.1 square into 12 gives you 0.376. So 0.376 kilograms, and with a negative sign because it is actually not present here. So please remember that in the end we have to sum these masses according to their signs. So 4.5 plus 3.392 minus 0.376 gives you 7.516, the sum of this column. Now we have to locate the center of mass of each of these subvolumes measured from point O. So the length of the rod is 1.5 meters, therefore its centroid or center of mass, because it is made up of just one single material, so centroid will coincide with center of mass. So measured from point O, its center of mass will lie at 1.5 divided by 2. which is 0.75. So 0.75 meter measured from point O is the center of mass of this rod. And now the center of mass of this outer disk, which is located at its center here, measured from point O. Uh, so this is 1.5 and plus zero point 0.3. So 1.5 plus zero point 0.3 is 1.8. So it is 1.8 meters measured from point O, the center of mass of the outer disk. The center of mass of the inner disk will also be at the same location, 1.8. The third column will be the product of the first and the second column. So 4.5 into 0.75 is 3.375, 3.392 into 1.8 is 6.1056, and minus 0.376 into 1.8 is minus 0.6768. So we have to sum this last column as well with respect to its signs. So 3.375 plus 6.1056 minus 0.6768 gives you 8.8038. So this is how this table has been constructed based on these sub volumes and the information provided in this figure. So the center of mass of this composite volume, entire composite volume, will be equal to summation uh, of this last column divided by summation of this first column. So it will be 8.8038 divided by 7.516, that gives you 1.1713. So measured from point O, y bar, okay, this distance up till G is 1.1713 meters. So since we have calculated the center of mass of this composite volume, we are now in this position to calculate the moment of inertia of this entire body about this axis G, about the axis passing through G. Okay, so we suppose that these formulas are actually given to us, known to us. Okay, so this 1 by 12 ml square represents the moment of inertia of this rod, cylinder rod, about its own axis, about its own center of mass that we have already located. It was at 0.75 meters measured from point O. So about this, about its own centroid or center of mass, the moment of inertia of cylinder rod is 1 by 12 ml square, where m is the mass of the rod, and this L is the distance measured from point O. So it's not the distance measured from point O, but this L is the length of the rod, the entire length of the rod, which is 1.5 meters. So this formula is a standard formula for rods that has cylinder rods. Okay, and for disc, the moment of inertia measured about its own center of mass, which is located at its center right here. So you have to draw the axis that is passing from the center at this point. The moment of inertia of a thin disk is given by half mr square. So this r is the radius of the disk and m is the mass of the disk. So this is the moment of inertia of thin disk measured about the axis that passes through its centroid. So we see that each of this axis is basically separated by some distance, some perpendicular distance. Okay, all these axes are parallel to each other. So this suggests us that we have to use the parallel axis theorem to calculate the moment of inertia of this entire volume. So for rod 1, we will going to now consider, we will going to apply the parallel axis theorem on rod 1, that is volume 1 or constituent volume 1 of our uh, body. So remember that moment of inertia, the parallel axis theorem has the same sort of formulation for moment of inertia as it was having as it was in case of second moment of area. The only difference is that in place of the area, now you are using mass. This d is still the distance, perpendicular distance between two parallel axes, and this one is the moment of inertia measured at the centroid of the rod, that is this axis. So for rod, okay, so for rod, the distance between the this axis that is passing from the centroid of the rod and this axis that is passing from the center of mass of this entire volume, okay, will be this distance, and this distance will be this value minus this value, which is 0.75. So we have simply 1.1713 minus 0.75, and this gives you the distance between this axis that is passing from the point G, center of gravity of this entire volume, and this point which is passing from the centroid of the rod. So you just have to subtract 0.75, which is the centroid of this rod, from the center of mass of this entire volume to have this value. Okay, so this is given as 1.1713 minus 0.75, which gives you 0.4213. Okay, so ICM1 will be given by this formula. So mass we have already calculated for rod in our table, that was 4.5 kilograms, and the length of the rod is 1.5 meters. So 1 by 12 m L square plus mass, which was 4.5 kilogram, and the distance between the two axes 0.4213 square. So this was 0.4213, so it has been squared here, and this gives us the moment of inertia of this rod about the axis that is passing from G. So this subscript 1 tells us that this is the moment of inertia of constituent volume 1 about an axis that is passing from point G, and that is equal to 1.64175. Similarly, you will going to apply the parallel axis theorem on this outer disk. So the subscript that I am using for outer disk, it is 2. It was my second constituent volume. So Ig2 will be equal to ICM2 plus M2D2 square. Here ICM2 is the moment of inertia of the thin circular disk about its own centroid, which is given by 1 by 2 mr square. And D is the distance between this axis that is passing from the centroid of the disk and this axis that is passing from point G. Okay. So we know that from this point, that is from point O, this is 1.5, and this was plus zero point 0.3. So it was about 1.5 plus zero point 0.3. So 1.5 plus zero point 0.3 gives you 1.8. So the distance measured from point O to the centroid of this disk is 1.8. Okay, and the distance from point O to this point G is ym. Okay, so it is 1.8 minus 1.173. So D2 is 1.8 minus 1.173, which gives you 0.6287 meters. Okay, so this distance this distance is 0.6287. The distance between the centroid uh, of the thin disk and the centroid of the the center of mass of this entire volume. So you substitute all the values here. ICM2 is given by 12 mr square, so half mass of the outer disk was 3.392 kilograms. The radius of the outer disk was zero point 0.3, so it has been squared plus 3.392 mass into 0.6287 square. That is the distance between the uh, centroidal axis of the disk and centroidal axis of the volume, given volume to us. And Ig2 is 1.4933 kilogram meter square. So similarly, you will going to calculate uh, the moment of second moment of area for this disk which is being subtracted, okay, about this axis. So everything will going to remain the same, only the mass will going to mass and radius will going to differ. So this ICM3 will be half mass of this third disk into radius of the third disk squared. So it is half 0.376 into 0.1 square. Please note that I am not using a negative sign here, because please remember that moment of inertia is never a negative number. So moment of inertia can never be negative. That is why you don't have to use a negative sign here. So it is half mass of the smaller disk 0.376 kilograms into radius of the smaller disk 0.1 whole square, plus mass of the smaller disk 0.376, the distance between the two axes. So this the distance between the axis that is passing from the centroid of the smaller disk and this axis that is passing from the center of gravity of this entire volume, that we have already calculated. It is 0.6287, so 0.6287 square, and this gives you the moment of inertia of a smaller disk about the axis that is passing from G. So you see that this is a positive number. I haven't used negative here. Even though the third disk does not exist, it has been subtracted. But this subtraction will be done in the end. So finally, the moment of inertia of this entire volume that was given to us originally will be the algebraic sum of all these moment of inertia that we have calculated. So we have calculated a moment of inertia Ig1, we have calculated moment of inertia Ig2, we have calculated moment of inertia Ig3. But we know that this third disk has been subtracted. So minus sign appears here with Ig3. Okay. So it is 1.64175 plus 1.4933 minus 0.1504. This gives you 2.984 kilogram meter square. So this is the moment of inertia of this composite volume about its own center of gravity G. 2.984. Okay. So please go through this question and don't bother about these formulas. They will be given to you in the exam, but you have to remember the parallel axis theorem and how it is being applied and what is the concept behind applying this parallel axis theorem. Okay, the rest of the calculations are just simple substitution of the results and simple addition and subtraction, right? So this is the moment of inertia of this entire volume that was given to us about an axis that is passing through the center of mass of this entire volume. And this actually represents the ability of this structure to resist angular acceleration about this axis that is passing from its center of gravity. So this is how you do calculations of moment of inertia for the composite shapes. Okay. The next problem is related with integration. So it is 10-97 of your textbook, and it says that determine the mass moment of inertia of the solid formed by revolving this shaded area around the axis, around the vertical axis actually. The density of the material is 7.85 milligram per meter cube. So it is 7.85, sorry, not milligram, it's megagram per meter cube. Now, you see that at once you can realize that function is given to you, that is z square equals to 8y, some sort of a function is given to you. So you have to use now integration to find out the moment of inertia of this solid about this vertical axis z. And you also notice that this z axis is the axis of symmetry, is the axis of symmetry for this body. It's a 3D body, okay? It's a three-dimensional body, it's a volume. Because moment of inertia has nothing to do with the area. It has to do with the body and with the volume. So again, you have to note that the given figure represents a volume. The volume is symmetric about the z-axis. So it is really symmetric about the z-axis. And we need to consider a differential disk element in order to find the moment of inertia for the given solid. So as you remember that in chapter number 9, when we were solving for the center of mass, center of gravity and centroid using integration, we used to uh, have a rectangular strip as our differential element, and using that differential element, the rectangular strip element, we were able to calculate the centroid, center of mass and center of gravity. But this is a three-dimensional volume, so we cannot use a rectangular strip here. Okay, we have to consider a differential volume, differential element that has a volume. So please remember that in case of moment of inertia, when you are using integration to calculate moment of inertia, you can use two types of volume elements. Okay, the first one is a disk, thin disk of some thickness dz. Okay, you have some thickness of this disk which is of differential level, and this actually has a radius r. So this is a disk element that we can consider while we are using integration. And secondly, we can consider a shell element. So a shell element is basically like a hollow cylinder. But you can notice that this shell element, since it has a finite height, okay, it is not a differential height, it has a finite height. And the thickness of this shell will be of differential level. But the height will be of finite dimension h. So therefore, this kind of a differential volume element is actually most often used for cylindrical geometries only. Okay, in this case, you see it has the outer edges of this 3D volume has a function. So it is not really, like a cylinder along its vertical direction. So this shell element cannot be considered here, but this disk element can be considered. Okay, it will very accurately going to follow this description of function that is given to us. Okay, so like this we will going to. So this disk intersects this function here, and as you will going to integrate along the z-axis, the thickness of this disk will going to vary and will going to capture this information. While it was not possible here in this case because the height is of finite dimension. So this shell element is only valid for cylindrical objects. Okay, where the dimension is finite along the length. Here it is defined by some kind of a function. So we're going to use disk element, and most often this disk element is used when you are using integration to calculate moment of inertias. But you have to notice one thing, that the this formula r square m, okay, oh sorry, r square dm, in this formula this r has to be fixed. Okay, if you remember that example that I gave you about a particle rotating about the vertical axis at a fixed distance r, okay, you you can realize that this r in this formula of second moment of area, sorry, moment of inertia, is almost fixed. So the entire mass remains at a fixed distance. However, this disk is actually a finite uh, body itself. So its mass is basically not, you know, it does not remain at a fixed distance, the mass, because it is made up of many, many particles. Okay, many infinite number of particles that will be located at different uh, radiuses, at different radii. Okay, measured from the axis of rotation, and so therefore this condition will not be fulfilled. Okay, so we have to first calculate the moment of inertia for the disk element. Okay, as it is a finite body itself, it's not a particle. So we have to establish the expression for moment of inertia for the disk element, our disk element, because it is not just one particle, it is a whole, it is a complete three-dimensional body itself. Of course, having a very small thickness. So let's proceed. So we have considered a disk element here having a thickness dz along the z-axis, and it has a radius small r. Okay, that is intersecting with this curve that defines the outer surfaces of this object given to us. So it is intersecting with this curve at point, at some arbitrary point. Okay, 0, y and z. So in the x we haven't actually moved um, any dimension in the x, so x is 0, but of course it is intersecting at this point. So this point is located at some distance y measured from origin. So this point is y, and this has a vertical dimension of z. So 0 y z is the point of intersection of this disk with this curve, and this is purely arbitrary. Okay, this disk can be here, it can be above as well, anywhere. So first of all, since we notice that this disk, the mass of this disk is not confined at one fixed distance measured from the z-axis, but it is distributed. So we have to first establish the formula for the moment of inertia of this disk measured from z-axis. So for this, we will going to consider our disk element, and we say that the disk has a radius of capital R, okay, measured from this axis z dash axis, and we have considered a ring element inside on this disk. So this is a ring element that we have considered, and using this ring element we can actually calculate the moment of inertia of this disk element. And you know what is the advantage of using this ring element? As I told you in the lecture, in the previous lectures, that the mass of this ring, all the mass of this ring is basically confined within its differential thickness dr, and so all the mass is actually located at one fixed distance small r measured from the z dash axis. Okay, now when this condition satisfied, when this condition is satisfied, I can use this formula to calculate the moment of inertia, because in this formula we have very clearly mentioned that this r is a fixed distance. Okay, so this formula r square m can only be used when all the mass is approximately located at one fixed distance from the axis, and that one fixed distance is the radius of this ring, that is a small r, and all the mass is confined within its small differential level thickness dr. So I can use this formula with confidence now, and using this formula I will be able to establish the moment of inertia of this disk, which is a finite body. So now this equation 1 can directly be used for the ring element, since all its mass is now approximately located at the same distance r from the z-axis. So we have Iz equals to integral r square dm, and now here we assume that uh, this disk has a density, areal density basically, okay, that is defined by mass per unit area. So it is kilogram per meter square. So we define the density of this disk in terms of per unit area. So it is kilogram per meter square. So sigma is density per unit area of the disk. Okay, so the mass will be equal to density times area, and this area is the differential area of the ring element, which is equal to 2 pi r into dr. So this 2 pi r is the circumference of the ring element that we have considered, multiplied by its thickness, and this gives us the area of the ring element, 2 pi r dr. So this dA is 2 pi r dr, and this sigma is the areal density. So we have integral r square sigma. In place of dA I can write uh, 2 pi r dr. Okay. So in place of dm we have substituted sigma dA, and in place of dA we have substituted the differential area of the ring element that we are using to approximate the moment of inertia of disk. It is 2 pi r dr. So r square sigma 2 pi r dr. Okay, so everything is constant, this sigma 2 pi, so we have r cube dr, integral r cube dr, that gives us r4 upon 4, and we will going to integrate between 0 and r, because this capital R was the radius of the disk. So we have half pi sigma r4 okay, because this r will become this r4, and this gives us half pi sigma r square into r square. So I have written this r4 in terms of r square into r square. And why I have written this? Because I know that this sigma was equal to the mass per unit area of the disk, and this pi r square is the cross sectional area of the disk. So this pi r square and this a will going to cancel out, and I will going to have this result left, that moment of inertia of a thin disk is equal to half m and square of its radius. So this is the same formula that we have used for disk elements in our previous problem that we just solved, and now it has been derived as well. So this is the moment of inertia of thin disk about the z-axis on, right? So on differential scale, because since I am using, you see, I am using this disk as my differential element to approximate the moment of inertia of this solid body given to me. Okay, so since I am using this on differential level, okay, I have to use this formula at differential scale. So at differential scale, just I have to apply d here. Diz equals to half r square dm, because in my original problem the disk has a radius of small r, so r square dm. So this m has become dm, and this iz has become diz on differential scale. Okay, and the radius of my differential disk is small r, so I have replaced this capital R square with small r square. So equation 2 can be used to estimate the moment of inertia of the given solid about the z-axis. Okay, so the moment of inertia of solid can be approximated by integrating this equation number 2, that is diz equals to half integral r square dm. Here dm is rho times dv, so mass is equal to density times the volume, and this will become half integral r square rho dv, and here dv is the volume of my differential disk, which is equal to its cross sectional area pi r square times its thickness dz. So in place of this dv I can write pi r square dz, and this will become r4 dz. This pi is a constant, it is the density of the solid given to me. Pi is a constant. Okay, so this will going to come out of the integration sign, and I will have integral r4 dz. So from the figure, okay, if you look back, this r, the radius of this disk, was equal to y. Okay, because this point where it is intersecting this curve, okay, this point has a coordinate y, so this r becomes equal to y. That is why I have used r equals to y here. So diz pi rho upon 2 integral, since r is equal to y, we have y4 dz. Okay, y4 dz, and since we see that we have to perform the integration with respect to z, this y has to be eliminated. So luckily the function was given to us, which was equal to z square equals to 8y, therefore y becomes z square upon 8. So we can substitute the value of y here, and this will become uh, so z square upon 8 will become 4 to the z raised to power 8 divided by 4096. So it is 8 raised to power 4 is 4096, right? So this 4096 is is again a constant, and it can be taken out of the integration sign, and it will be, when it will be multiplied with 2, it will become 8192. So pi rho upon 8192, and if you integrate this z raised to power 8 dz, you will get z raised to power 9 upon 9, and the limit defined on the z axis was from 0 to 4. So it was from, on the z axis the limit was from 0 to 4. So the limit was 0 to 4, and you integrate, you substitute all the values here. Okay, substitute all the values here, simplify it, it will become 11.170 times rho. 11.170 times rho, and rho is given to you as 7.85 megagram per meter cube. So you have to convert it into gram. 7.85 megagram means 7.85 raised to power 6 grams, and you have to convert grams into kilogram. So you divide it by 1000, and you get the final result. So the moment of inertia of this given solid about the z-axis is 87.685 raised to the power 3 kilogram meter square. Okay, so it is a very high value. So this is how you handle the problems of moment of inertia related with integration. You most of the time you always have to consider the disk element, okay? Because shell elements are only valid for cylindrical geometries that has non-functional formats along their length. For rest of the cases you have to consider the disk element. Okay. So you can notice that so this explanation was actually given to you just for the sake of your understanding. uh, However, you can start you know, you can start directly from this equation once you have considered the disk element for your problem, as I have done here. Okay, then you just need to know that the moment of inertia of the disk element about the axis of symmetry, that axis of symmetry of this given solid. Okay, that happens to be the axis of symmetry of this disk element as well, because it is passing from its center. So this uh, okay, so as you can see that this axis, z axis, is the axis of symmetry of the given solid, and it is also the axis of symmetry of your differential disk element, right? So you just need to know that the moment of inertia of your disk element relative to the axis of symmetry is given by this value, half r square dm. Okay, half this result actually, half mr square. So you can directly use this result to calculate the moment of inertia of your solid. So you can start from this heading, because you already know that the moment of inertia of the disk element about its own axis of symmetry is given by half mr square. So you just need to represent this on the differential level, which is half r square dm, and directly use this result for the solid given to you. Okay. So please go through these questions thoroughly. This has brought us to the end of chapter number chapter number 10, and now we are left with only one more lecture, and I'll going to briefly explain uh, the method of virtual work in my last lecture. Thank you.